Hey Wildcats, welcome back. This is Mr. Walk, and we are going to do another set of Algebra 2 notes. What we're going to be talking about today is function transformations. In our last set of notes, we were introduced to 5 different function families, and we saw the parent function. Now we're going to look at ways which we can transform those functions. The first thing we're going to do here is fill in a couple vocabulary words. And our first vocabulary word here is rigid. Rigid transformations keep the original shape and size of the graph unchanged. So the size and shape doesn't change, but the graph can move around, maybe up, down, left to right, or even be flipped upside down or flipped left to right. Those are what we call rigid transformations, and guess what? These are what we're going to focus on here. So this is going to be the main thing we're going to be looking at and working with our transformations. Now, the other type of transformation is non-rigid. Non-rigid transformations distort the shape of the graph. So it could stretch it out, or it could squish it. The graph could get skinnier or could get wider from left to right. Those are non-rigid transformations. These ones here, we'll talk about these in our notes, but you're not really going to see them in our assignments nor on our test. So just to let you know. Okay, let's take a look here at this first set. The first type of transformations we're going to talk about here are called translations. A translation is simply when the graph gets moved in one of 4 directions: up, down, left, or right. And the key concept that we're looking for here as we go through these notes on transformations is we want to know, how does a change in the equation affect a change in the graph? And we want to be able to connect those two together. So let's take a look here. We've got 4 cases. Now, for this first one, it's got a plus c. C is going to be some number, any real number. Here we have a minus c. Here we also have a minus c. And here we have a plus c again. Now, the thing to notice between these is that, let's just compare, okay, plus c here and plus c down here. These are not exactly the same thing, because on this one, the plus c is outside of the parentheses. Down here, the plus c is inside of the parentheses. These are actually 2 different things. They're going to give us 2 different types of translations. And what I want to do before we fill in over here the graph behavior, let's just write this here. This here is add, because we have plus, and we're going to say outside. This is terminology that we're going to be familiar with. Like, we're going to ask ourselves, are we adding on the inside or the outside of a function? Because that is going to determine how it's translated. Okay, this one here, this is subtraction on the outside. This one here, since it's inside of parentheses, that's subtract on the inside. And the last one here is add on the inside. So these 4 cases here correspond to our 4 directions: up, down, left, and right. And let's go ahead and label these here. I'm just going to label it with the arrow, and then we'll spell it out here. But when you add on the outside of a function, this is going to move the graph up. When you subtract on the outside, it's going to move the graph down. When you subtract On the inside, it's going to move the graph to the right. And when you add on the inside, it's going to move the graph to the left. Now, these ones here are a little backwards from what you might think. Because you might think, okay, if I'm subtracting, that's negative. If I'm going left to right on the x-axis, to the left is negative. Okay, but this actually works backwards from what you think. When you subtract on the inside, it doesn't move the graph to the left, it moves it to the right. So I just want to make that clear. Okay, and then what we'll do is we're just going to spell these out, and we're going to use our vocabulary words. So our vocabulary word for move the graph is translate. So here I'm going to say translate up. And here I'm going to say translate down. Translate right. And translate left. Okay, so when you hear this word translate, all that means is move the graph in one of these 4 directions. Okay, our next type of transformation, which also falls in the category of a rigid transformation, is a reflection. All right, now reflections happen when we introduce a negative sign. Now note that this is different from subtracting. We're not subtracting, we're actually making the function negative, either by putting it here on the outside or by putting a negative sign here on the inside. So we'll write this out here. We'll go negative outside, and here we have negative inside. Okay, this is going to result in a reflection, which is just a flipping of the graph. Now there's 2 ways that the graph can be flipped. The graph can be flipped from top to bottom. So we'll do this. You know what we'll do? We're going to write it 2 different ways. We're going to say here flip top to bottom. And then what we're going to do is we're going to write this again using our vocabulary terms. Actually, the correct way to say this using our correct vocabulary is going to be reflection across x-axis. Okay, so when we reflect a graph across the x-axis, that's the same thing as flipping it from top to bottom. Okay, now when we have a negative on the inside of the function, this is going to result in a flip from left to right. And the way that we're going to say this with our vocabulary words is reflection across the y-axis. Okay, those are our reflections. Okay, so next we have our non-rigid transformations. I'm just going to briefly go over this, but this is not going to be on our assignment or on our test. So just so you know, we're not even going to be doing this, even though we'll look at it here on the notes, but you're not going to have to do it on the assignment or the test. But it is good to know. Okay, so our non-rigid transformations are going to be either a stretch or a shrink of the graph, and this happens from Hey, notice what we have here. Now look, our number C, so this can be some number, any number. And take a look, it's being multiplied. Right, so it's multiplying the function. So this is multiplication on the outside. This is multiplication on the inside. We can write these down here. Multiply outside, multiply inside. Okay, and when we do this and our C value is greater than 1, what happens is we get a vertical stretch. So it means the graph gets stretched from top to bottom and it becomes more skinny looking. And when we do this here and our C value is between 0 and 1, so it's a number less than 1, but it's still positive, then here we're going to get a vertical shrink. Or another way you could say this is a vertical compression. So if we compress the graph from top to bottom, and then it gets wider left to right. So we'll see some examples of those here, but again, you don't really have to worry too much about those. Okay, look, let's take a look at some examples. Okay, in example number 1, we have two functions that we're going to graph here. And, we haven't talked about this kind of notation yet, but just so you know, when you see this f of x, that's the same thing as y. So this is the same thing as writing the equation like this: y equals absolute value of x. This is another way of doing it, and it's called function notation. And sometimes it's convenient because, like in this instance, when you have two different functions, we can give them different names. So this first function is called f, and our second function is called g. But it works the same way. So just wanted to point that out. We'll talk more about function notation. But let's take a look here, and let's graph both of these functions. So our first one, f of x equals x. So this is like our y equals absolute value of x. This is like our y equals absolute value of x. Now you can refer back to our last notes. You should probably have those notes out. That would be a convenient reference. You can look at the graph of the absolute value. It looks like this. It's got its starting point at 0, 0. And then if you remember this one, this is the V shape. The V in the word value is your reminder that absolute value has a V shape. That's the graph of the parent function. Now let's take a look at the second one here, g of x. Okay, what's different about this? It's still an absolute value, but now it's got plus 2. All right. The thing we need to ask ourselves is the plus 2 on the inside or is it on the outside? And I'm telling you here that this one is on the outside. If it were on the inside, it would be inside of the bar. So it would be like this: absolute value with the x, and then the plus 2 on the inside, and then close the absolute value. This is an example of inside, but that's not what we have. We have plus 2 on the outside, and you know what? We can reference back up here. Let's see what happens when we add on the outside. So this is basically what we have. Add on the outside, and look, it's going to move the graph up. Translate the graph up. So that's what we're going to do here. We're going to end up getting the exact same graph, except it's going to be translated up 2 units. So let's go ahead and write it down here. This is what I want you to do. Write down the transformation. So we're going to say translate 2 units up. How do I know it's 2 units? Because it's a plus 2. If it were plus 5, it would be 5 units up. Okay, so what this means is now our starting point, which was originally right here for the parent function, is going to be scooted up 2 units. And every other point is also going to be scooted up 2 units. So guess what? These are the points we get. And this is the graph that we get. Exact same shape, still a V shape, but now it's been translated 2 units up. Okay, example number 2. Here's our parent function. G of x equals x squared. This is a quadratic, and x squared is the most simple quadratic we can have. This is what it looks like. Again, you have this in your notes from our previous class, from our parent functions. It's got a point at 1, 1, and then at 2, 4. And then it's got a point at negative 1, 1, and negative 2, negative 4. This is the one that's not a V shape, but instead it's a U shape. It curves at the bottom. There it is. Okay, now our second function, h of x, is right here. Okay, let's take a look and see what's different. Well, it's still x squared, so it's still the same function family, a quadratic function, but it's got minus 3. Is the minus 3 on the inside or the outside? This, again, is the outside of the function. Hey, if you want to know what it would look like if it were on the inside, so when you have a quadratic and you want a minus on the inside, that means you got to put the subtraction in parentheses and then you put the squared like that. This is an example of subtracting on the inside. That's not what we have. We have subtracting on the outside. If we reference our notes up here, subtract on the outside is going to translate the graph down. So here we're going to say translate 3 units down. And again, it's a 3 because our number there is a 3. So now all we're going to do is take our parent function, the blue graph, and each of those dots, each of those points is going to drop down by 3. So our starting point, which was at 0, 0, is going to drop down to here, 0, negative 3. This point is going to move here, here, and then we're going to have here and here. Okay, and we get the exact same graph, still the same shape. If you remember the name of that shape, it's a parabola. So we still have a parabola, except now it's been translated 3 units down. Now on to example number 3. And our parent function here, f of x, is x cubed. Hey, just a reminder, when you have an exponent of 3, that's a cubic function, x cubed. So that's our parent function. Let's go ahead and graph that one. That's got a point at 0, 0, 1, 1, and 2, 8. You know what? This is going to be off the chart. I'm just going to put it up here. Let's see. 5, 6, 7. It would be somewhere up here. 2, 8. And then we got a point at negative 1, and negative 2, negative 8. So that would be, just going to eyeball it somewhere, I'll say right here. Okay, and I'm going to connect these points. The cubic graph is also a curved graph, although it looks pretty straight here. I mean, it's just coming up really fast. As it gets close to 0, it kind of flattens out, and then it curves back up again. It keeps going up. Put arrows on both sides. That's our parent function. Now let's look at the second function we're giving. G of x is equal to x minus 2 cubed. And notice here, our subtraction, is that on the inside or the outside? Well, when it's inside parentheses like this, it's on the inside of the function. So here we're subtracting on the inside. If we want to reference our notes, when we subtract on the inside, the graph translates to the right. That's what's going to happen here. Let's write it down here. Translate 2 units to the right. And now let's go ahead and do it. So basically each of these points is going to move to the right 2 units. So the starting point, which was at 0, 0, is now going to be at 2, 0. And then this point here will scoot over to here. This point here will scoot over to here. And then we've got these points that are off the chart. So that's going to scoot over to approximately right there and approximately right here. And then we'll connect these with the smooth curve, same shape. And let's see, let me try that again. I'm going to try it one more time. Okay. Here we go. We flatten out as we hit the middle point and then curves back up again. Put arrows on the top and the bottom. And there we have our original parent function in blue, and then our green function, which has been translated 2 units to the right. Same shape, just scooted over by 2. And now example number 4, and parent function g of x equals the square root of x. You guys remember what the square root function looks like? Hey, if not, that's okay. You took notes on it. Take a look at your notes. Okay, our notes will show us that the graph of the square root function starts at 0, 0. It's got a point at 1, 1, and then it's got a point at 4, 2, and it starts from here and it curves up and to the right. Put an arrow there. It's going off to the right. However, there is no arrow on the left side because it stops right there. This function does not go into negative territory with the x value. That's actually where we have undefined. Does not exist. Okay, so there's our parent function square root. Now let's take a look. H of x. In here we also have a square root function, but it has a transformation. It has a +3. Now look, is that inside or outside? And maybe I'll point this out to you here. This is on the inside of the square root. The way you can tell is where the top of the square root line ends. So notice the square root symbol goes all the way over here and it's hanging over the 3. It's important to see this because since the square root symbol is over the 3, that means the 3 is on the inside. If it looked like this, square root of x, and it stopped, and then you had +3, that would be +3 on the outside. All right? We've got +3 on the inside, and now we can reference our notes if we want. When we add on the inside, it moves the graph to the left, so that's what's going to happen here. We're going to translate left. And it's a 3, so it's 3 units. So we'll write this down. We'll say translate 3 units to the left. And what that means is each of these points is going to move 3 to the left. So our starting point is now going to be here at -3, 0. And then this point will move 3 to the left, and this point 1, 2, 3. Here it is. And there is the graph of our translated square root function, translated 3 units to the left. Okay, next up, example number 5, and it says here, finding equations from graphs. So take a look here. We're starting off with the graph. They're showing us the graph, and they want us to find an equation. It says here the graph of the parent function f of x equals absolute value of x is translated in each of the graphs shown below. Find an equation for each of the transformations from the parent function. Okay, let's take a look at 5a. Now they tell us here that it's absolute value, but even if they didn't tell us that, we should be able to identify from this shape, this is a V shape, this is an absolute value graph. Now this one here is definitely not the parent function because the parent function has its starting point at 0, 0, and then it goes like this. So how has this one been moved? Well, it's gone 1 unit to the right and 2 units down. Okay, so it's been translated 1 unit to the right and 2 units down. So let's reference what we have up here. So we're going to the right and we're going down. So going to the right means I need to subtract on the inside. Going down means I need to subtract on the outside. So this is what I'm going to have in my equation. Subtract on the inside and the outside. Let's do it here. This is the parent function. And let's see, they called it f of x. Okay, so we'll keep the same lettering here. F of x equals absolute value of x. That's the parent function. Now, the translated function, we'll call this one g of x, is going to be, okay, so 1 unit to the right. Going to the right is subtraction on the inside. So that needs to be in between the absolute value bars. So this is what I've got. Absolute value of x, but don't put the other bar right here. We need to have actually some space in there for subtraction. We're going to minus, and since we're only moving 1 unit to the right, we're only going to subtract 1. Okay, now the graph is also shifting down 2 units, so that's subtraction on the outside. Subtraction on the outside just comes at the end, so that's going to be a minus 2 here. And this is our answer. This is the equation of the graph. Example 5b. Here is another graph. Now this one is also an absolute value, and I can tell because this is a V shape. But if you notice this V shape, this is actually an upside down V. This is an upside down V. So we're going to have to take that into consideration when we write our equation. Okay, so remember the parent function was going to have its starting point, or in other words, the bottom of the V right there. And then it's going to look like this. Okay, but this one has been translated 2 units to the left and then 3 units up. Okay, but that's not all. If it was only 2 to the left and 3 up, then we'd have a V right here opening up. But we actually have a V opening down. So the fact that it's flipped upside down, we put this in our notes here. This is a reflection, okay? Here it is, okay. When we flip top to bottom, or what we also call a reflection in the x-axis, that is the result of a negative on the outside of the function. So we basically have to put a negative in front. Okay, so let's do that here. Let's write our equation. So I'll write the original parent function, f of x equals absolute value of x, and then we'll go here, we'll call this one h of x equals, okay, we need the negative sign up front. So this is what we're going to have here. We're going to have absolute value of x. We're going to leave some space for something on the inside. Let's put the negative sign out front. Negative sign out front gives us the reflection because the V is upside down. And now let's see here. We've got 2 units to the left. So if we're translating to the left, that's addition on the inside. This is going to be a plus 2 on the inside, and then up 3 is going to be a plus 3 on the outside. So there it is. There's our equation. Negative out front, plus 2 on the inside, plus 3 on the outside. Okay, example number 6. Compare and contrast the graph of square root of x with the following transformations. Consider changes to the domain in each case and sketch the parent and each function. Okay. All right, so let's see here. This is the function we've got. G of x equals negative square root of x plus 2. Let's also write down our parent function. I guess maybe we don't have to write it. It's already written here. This is our parent function. It does want us to sketch the graph. So let's start by doing that. The parent function is always like the most basic. It's the starting version of the graph. And there it is. Okay, now g of x, what does it have here? It's got a negative on the outside. And it's got a plus 2 also on the outside. Okay, notice the plus 2 is not on the inside. If the roof were all the way over there, if the square root roof looked like that, that would be on the inside, but that's not what we have. So this is plus 2 on the outside. So let's do this. And maybe I'll make a little note to myself here. I'm going to say reflect x-axis, or in other words, flip top to bottom, and then plus 2 on the outside. You can reference the table that we put on the other page. When you add on the outside, that's going to move it up 2 units. So I'll just do this here. I'll put a little arrow for up, so we're going to translate up 2 units. Okay, and now let's sketch the graph. So my starting point, instead of being right here, is translated up 2. So it's going to start here. Okay, now, instead of the graph going up and to the right, since it's been reflected in the x-axis, that means that it instead of going up, it's going to go down. So this one is going to curve down and to the right, and it's going to look like this. There it is. Okay. So let's see, we've got the graph sketched of the parent function and g of x. Oh, it also says this. Okay, consider changes to the domain in each case. All right, well, what do you think? Does the domain change here? And just a reminder, domain is all x values of the function. Okay, for the parent function, square root of x, the graph stops right here. It doesn't go any further than this point. Okay, so, and for domain x values, we're talking about going left to right. So how far to the left, how far to the right? Well, you know what? This graph doesn't go any further to the left than right here. This is as far to the left as it goes. And that's an x value of 0. So my domain for the parent function, this is what I'll write here. Furthest to the left it goes is 0. And then furthest to the right, well, it goes on forever. That arrow there means the graph goes forever. This is a positive infinity. The infinity always gets a parenthesis because it's an excluded value. The graph never actually touches infinity. But the 0 gets a square bracket because it's an included value. The graph does indeed touch an x value of 0. Okay, so what about the domain of this guy here, g of x? Well, if we take a look at the graph left to right, you know what? This is still as far as the graph goes to the left. Notice that the domain actually doesn't change here because the graph didn't get shifted left or right. It only got shifted up. So this domain is going to be identical. Okay, the furthest to the left it goes is a 0, and then the furthest to the right it goes, well, it goes forever, so it's an infinity. So our domain for g of x okay, next one, 6b. Our function is h of x equals the square root of negative x. Okay, now they still want us to do the same thing. Let's graph the parent function. So we'll keep the parent function again in blue. So this graph is the graph of square root of x. And then next we'll do this one here. So the only thing that's different between this one and the parent function is, of course, the negative sign. And this negative sign is on the inside. Okay, so if we want to go check our notes, let's see here. A negative. Hey, look, a negative on the inside flips the graph left to right, or in other words, a reflection in the y-axis. Okay, so let's just label it here. We'll say reflect y-axis. Okay, that's what's resulting from the negative on the inside. That's the only transformation here. So this is what we're going to have. Our parent function starts at 0, 0, and our new function h is also going to start at the same point, because notice the starting point didn't get translated. We're not moving the graph up, down, left, or right. It's still starting from the same point. But now instead of going up and to the right, it's going to go up and to the left, because it's been reflected across the y-axis. It's been reflected from right to left. So here it is. We'll have a point here and a point here. And there is our graph. And again, let's compare the domains. So the domain of f of x, just like we saw before, 0 is all the way to the left, is the furthest that the graph goes to the left, and then it goes out to positive infinity on the right. Okay, right here the y-axis is a brick wall. For the blue graph, it doesn't go left of that red line. Now, with the green graph, our h of x, square root of negative x, notice that that red line, the y-axis, is as far as the graph goes to the right. And then what does it do? It goes to the left forever. So how are we going to write this domain? Okay, so when we write the domain, it's always the furthest to the left and then the furthest to the right that the graph goes. Now, this graph goes forever to the left, right? That's what this arrow means. It keeps going to the left forever. That's the negative direction on the x-axis. So that's going to be a negative infinity. Okay, and then the next thing we have here is how far does the graph go to the right? Well, we just saw that's the y-axis. It doesn't go any further to the right beyond that point, and that is an x value of 0. So we're going to have this. Infinity always gets a parenthesis. It's an excluded value. And here, the 0 is an included value because the graph actually touches an x value of 0. And there we have our domain. So notice that these domains are not the same. Okay, now example 6, part C. All right, let's do this one last time here. Let's graph the parent function, square root of x. That's this graph. And let's compare that with this function here, k of x. And what do we have here? We've got a negative on the outside. So this is going to be a reflection in the x-axis. Reflect x-axis. Again, that's flipping the graph from top to bottom. And then we also have plus 2 on the inside of the square root. Okay, so when we add on the inside, that moves the graph to the left. So this is going to move the graph left 2 units. Write it like that. So 2 units to the left. Okay, so let's go ahead and sketch this graph. So it's being translated 2 units to the left. So I'm going to take my starting point and move it 2 units to the left. 1, 2. Now this is the starting point. And reflect in the x-axis, so it's flipped top to bottom. So instead of going up and to the right, it's going to go down and to the right. So we'll have this here, and then 1, 2, 3, 4 here. This is the graph that we're going to have. That there is the transformation. And our domain for our parent function is not changing. That's 0, infinity. And again, that's because for our parent function, this is like the brick wall that it never goes past. As it goes to the left, the blue graph never goes to the left of that line. For the green graph, it's actually here. This is as far left as the graph goes. It never goes any further to the left than there. And what's the x value there? It's a -2, right? -2. So -2 is going to be lowest x value, or in other words, our furthest point to the left. And then to the right, hey, look, the arrow means it goes on forever. So it's still going out to infinity. Infinity gets parenthesis. The -2 gets a square bracket because it's an included value. The graph actually touches -2. And hey, there we're done with example 6. Okay, so next we've got example number 7. Now, you know what? In example 7, this is where we look at some examples of non-rigid transformations. This is the stretch and the shrink. And for sake of time, I'm not even going to go over these just because you're not going to have to do this on your assignment or on your test. So don't worry about these for right now. Although if you're curious, this would be good for you to try, and you could use Desmos graphing calculator just to take a look. It would be worth your while to take a look at that. But again, it's not going to be on the assignment or the test, so I don't want to waste our time. We're not going to do those right now. Let's just skip ahead and combining transformations. Now there is some vertical stretches in here, but that's okay. We're still going to do these because here what we're doing is we're just writing the equation following each of these transformations. So find the function that is finally graphed after the following transformations are applied to the graph of y equals x squared. Show each step. Okay, so we start with this y equals x squared. Here it says shift 1 unit to the left. So if we're going to the left, that means we have to add on the inside. So my function is then going to look like this. Y equals, to go on the inside of a quadratic, you have to do parentheses. 1 unit, so it's going to be a +1. Okay, here it says vertical stretch by a factor of 2. Okay, if you look up in the notes, vertical stretch by a factor of 2 just means we're multiplying by a 2 in front. So this is what we'll get next. Y equals, this is what we've got, x plus 1 squared multiplied by the 2 in front. And then it says a vertical translation 3 units down. To translate down, we have to subtract on the outside. So what we have so far, 2x plus 1 quantity squared. And now we want to translate 3 units down, so subtract 3 at the end here. There it is. There's our equation. And example number 10. Find the function that is finally graphed. Okay, applied to the graph of y equals x squared. Okay, show each step. Number 1, reflect about the x-axis. Okay, so we're starting with y equals x squared. To reflect across the x-axis, that means we need a negative sign outside of the equation. And when you put a negative outside, that means in front. So right here in front. Okay, and then we're going to shift to the right 3 units. So to shift to the right 3 units, we have to subtract on the inside. So let's do this. Y equals negative x squared. But now look, if we're going to put this on the inside, it has to go in parentheses. So we'll go parentheses squared there. And then we can go minus 3 on the inside. There it is. And then the last piece here, shift down 2 units. So to go down 2, we need to subtract by 2 on the outside at the very end of the equation, and it's going to look like this: negative x minus 3 squared. Then at the very end here, we'll put minus 2. There it is. There's our equation. Okay, let's go ahead and finish up here with the summary. What we're going to do on our summary, we're just going to write in here the transformations that we're going to be using, so the rigid transformations, and I'm going to try to write this in a condensed form, and we'll see if this makes sense. So I'm going to put the word outside, and then I'm going to put here a plus and a minus. What I'm referring to here is the equation. So outside of the equation, if I add, how does this move the graph? Translates up. And if I subtract on the outside, it translates down. Okay, on the inside of the equation, we can either add or subtract. If we add on the inside, this is potentially backwards from what you might instinctively think. Okay, when you add on the inside, it actually moves the graph to the left, and when you subtract on the inside, it moves the graph to the right. Okay, and we can just make a little note also about our reflections. So this comes from a negative, so we'll say, maybe we'll just do this, we'll abbreviate it as negative on the outside, and this is a reflection in the x-axis, but we'll just write this in a way that we can remember it, maybe, or not using our vocabulary words, but we'll write it like this. We're going to say flip top to bottom. And then our other reflection comes from a negative inside of the equation, and that gives us a reflection in the y-axis, which is a flip left to right. And you know what? I guess we'll also do this. We'll add this. So this is going to be, I said we weren't going to do it, but we'll say it here. So this is going to be reflection, and I'll just abbreviate it, reflection in the y-axis, and this here is a reflection in the x-axis. And this is just an abbreviated form of what we put at the top. Hopefully that kind of makes sense, but that's our summary. This is really what you need to know here in regards to our function transformations. Hey, thank you for sticking with me all the way to the end. Please let me know, or let your teacher know, any questions that you have about any of this stuff, and I'll see you next time. Take care.